Welcome to the pre-recording of the second half of lecture 20, scheduled for the very end of week 7 in our 8-week summer course, Introducing Computer Algorithms. We are going to consider an application of the Hamiltonian cycle problem, which we have shown to be NP-complete. The traveling salesman problem is also NP-complete. So we have done a lot of work already in the previous lectures and also in the first half. So this more general problem will actually go faster. So to make this lecture self-contained, let us consider the terminology. So we have classified algorithms. We have said that an algorithm is efficient if we know that, if we can prove that the worst case running time is bounded by a polynomial in the input size. So we are doing a number of elementary steps that is polynomial, that is a polynomial function in the size of the input. Then all problems for which we do have efficient algorithms is collected. All those problems, they are collected in the set which we call P. The set NP is very much similarly defined, but we replace the word algorithm by certifier. A certifier verifies whether any given output, any given string that satisfies the output formulation for a problem, whether that actually is a valid solution. And it has to be efficient. So we want also an algorithm that runs in polynomial time. So of all the problems for which we have an efficient certifier, but not necessarily an efficient algorithm, the most important problems of those type of problems are called NP-complete. Because if we would have an efficient algorithm for NP-complete problems, there wouldn't be any difference between having an efficient certifier and having an efficient algorithm. So of all the hard problems for which we can still verify in polynomial time, the NP-complete problems are somehow the most important ones. So we have to show first that if we have a new problem, that if that problem is NP-complete, we first have to show that there exists an efficient certifier. Then the hardest step there is to show that there is an NP-complete problem that can be reduced in polynomial time to our new problem x. So this slide makes the lecture self-contained. It kind of states the framework in which we will view the traveling salesman problem. Here is then the traveling salesman problem. We have a directed graph. You could consider the vertices in that graph as cities which must all be visited. The cities are connected by roads. Here in this example there are two directional, and I have added the same weights as the distances. It should not necessarily be the case. But here now the problem is to compute a tour that visits all these 4 cities, and so that the sum of the edges that you visit is actually smallest. So if you want to solve this problem economically, you're interested in the tour with the smallest length. So in the practical sense, this is again an optimization problem. We can reformulate this in a decision problem, because as we have seen, any optimization problem can be reformulated as a decision problem. If you can solve a decision problem efficiently, then you can ask your black box to solve the decision question in a kind of binary search fashion. So that's why we focus on the decision problems in this course, in this part of the course. So we are then adding an additional number to the input. So we ask for the weighted and directed graph given on input. We ask, is there a tour where the length of the sum of the length of all the edges that you visit, so the sum of the distances, is that bounded by that D? So here for our running example, we see that there is a tour visiting all the 4 cities where the sum of the distance traveled along the edges equals 7. So if you give this graph on input to our algorithm, which decides the traveling salesman along with the bound 7, you will have the answer yes. And you can always call any black box solver a polynomial number of times. So even if the D would be any number with kind of divide and conquer in the binary search, you can quickly narrow it down. Okay, so this is an important problem, and important problems deserve our attention. So, can you figure out a solution to this traveling salesman problem? Develop an algorithm to solve the traveling salesman problem. This is a sequencing problem, and essentially one algorithm would be to list all the permutations of the cities. So if there exists a tour, then this tour should be part of any permutation. So we are interested in an algorithm, and an algorithm is well defined, bounded in running time, so it will terminate. You will list all the permutations, and it is also correct. So if there is a tour, you will simply generate all permutations and check the length. So checking the length that we will do as well is actually polynomial time, although of course the size of the set of all permutations is factorial in the number of vertices. So the worst case running time of your algorithm is actually n factorial of that type of algorithm. You are certainly more than welcome to consider other choices. So you can think of applying dynamic programming to this. So a variation of this question would be apply dynamic programming. So you consider any vertex. And in some sense, if you think about efficiency already, the vertex should have at least one edge coming in and one edge coming out. So you actually consider that vertex as a part of a cycle, and then you can ask what happens if you consider the graph with that vertex and all the edges connecting it to the rest of the vertices. If you had a tour in the reduced graph, how would you combine that tour with all the edges that you add again, that leading to that first chosen vertex? So that's already a very interesting exercise applying dynamic programming. So we are going to start review in the next week. Also, there is the important class of branch and bound algorithms. So does the size, the bound D actually help? So it could very well be that if the size of D is rather large, is rather small, and you have edges, cities that are very far apart from each other, you would eliminate already many of the edges. And that would already significantly reduce the complexity of this problem. So we will not, you should not be able to find an efficient algorithm for efficient in the sense of this course, but you could still discover a lot of interesting properties for this important problem. Okay, we our task is to show that the traveling salesman problem is NP complete. And what problem will be select? Well, we have studied the Hamiltonian cycle problem extensively in the first half of this lecture and demonstrated that the Hamiltonian cycle problem is NP complete. So the Hamiltonian cycle problem takes on input a directed graph and asks, so it's again a decision problem, is there a cycle that visits every vertex exactly once? So the cycle corresponds to the tour, which is the terminology that is used in this traveling salesman. It's only now that for the traveling salesman problem, you need to have distances. But it seems obvious if you can solve the traveling salesman problem, you can actually solve also the Hamiltonian cycle problem. Um, so first things first, so we have to show that the traveling salesman problem is in the set of problems for which there exists an efficient certifier. So what is a certificate for this problem? Well, if you know all the cities, the order in which the cities are visited, then actually you can claim that this sequence of cities actually constitutes a tour. And the certifier needs to verify that indeed you are visiting every vertex exactly once, so it represents a permutation. That can be done in time proportional to n. You just have to keep track of which cities that you visited as you go through your list of vertices. And you also, at the same time, you can actually add up the distances between two consecutive vertices and see at the end if the length of that tour is bounded by that bound D. Um, in the Hamiltonian cycle problem, we didn't specify the data structure, so it could just be a list of all the edges, that's fine. But here suppose that we are using an adjacency matrix. And if two vertices I and j are connected, then at the ij position in the matrix, you have the weight, the distance between those two. And therefore, looking up into an adjacency matrix is constant time. So the running time of your total algorithm depends only on the number of vertices. And that's a very efficient algorithm. So we do have an efficient certifier, and the lemma shows that our traveling salesman problem is in the set NP. Great, first hurdle cleared. Now we have to show that the problem is NP complete. How are we going to do this? Well, the main result of this second half of this lecture 20 is actually that the main theorem here. The problem is in the set NP. We do have an efficient certifier by the previous lemma. And the problem that we choose that is already NP complete by all the hard work that was done in the first half of this lecture, we will choose the Hamiltonian cycle problem. The Hamiltonian cycle problem then needs to be shown that any arbitrary instance of the Hamiltonian cycle problem can be solved by the traveling salesman problem. And the transformation of the input of the Hamiltonian cycle problem can be done in polynomial time. That's the general strategy applied. Okay, we have to define a graph for the traveling salesman problem, which expects a directed weighted graph. So we have to add weights. And here is what we propose. So this is the algorithm, and it's obvious that this is running in um, polynomial time. So what we will do is, if there is an edge, we will add weight 1 to the new graph. If not, then we will actually set the distance in this weighted graph to 2. So actually we will construct new edges. So if the directed graph G prime will actually have more edges. So for any pair of two vertices, we will actually construct an edge, but the length of these two edges will be so high that we won't pick it. So we have defined the graph G prime. We also need to pick a bound on the total length of the tour. And that length of the tour will actually be the number of edges, because all the edges that were in the Hamiltonian cycle graph are actually 1. So the length of a Hamiltonian cycle will therefore be n if we visit all the n vertices. So we have the n minus 1 in the path from the first to the last, and then we come back. So we have n. So you can already see that the solution of the Hamiltonian cycle will lead to a tour of length n. That should be obvious from this construction. Polynomial time reducibility is important, so we are adding n square, and it's O(n) square, so back and forth if you like, but it suffices that we have only directions in one. Okay, here is now to make sure, so in some sense not all exercises are equal in difficulty. How can you encode the graph that we have used in the traveling salesman problem? How can you now encode this? So this is a graph where I have removed all the distances. Encode this as a traveling salesman problem. And this exercise seems quite trivial, but also verify now that if you have a path, if you have a Hamiltonian cycle in this graph, you also essentially have a solution to the traveling salesman problem. Okay, and actually it's the important direction back. So we are going to try to solve the Hamiltonian cycle problem by the traveling salesman problem. So it's actually the opposite direction that matters most. All right. I indicated already one way. If you have solved the Hamiltonian cycle problem, if you have a solution of the Hamiltonian cycle problem, then you can also, in that G prime graph, you have a tour of length n. That's actually very straightforward in the proof, going from left to right in the if and only if. We have by construction that the edges, if there was an edge in G, then in G prime there will be an edge of length 1. So we do have a tour of length n in G prime. So we have solved the Hamiltonian cycle problem. On the other hand, if the Hamiltonian cycle comes up with a tour of length n, then we can show that there is a cycle. So the tour visits all the vertices. So, and the length is 1. So that means that we could not have visited any edge of length 2. Um, so we have visited only those edges that were already in the original graph. So therefore, we do have a cycle in the original graph. That's it. So there is an equivalence between the problems. And that actually proves the fact that the Hamiltonian, that the traveling salesman problem is NP complete. Okay, so let's see another extension. So we have already shown that the traveling salesman problem is NP complete. There is something called the Hamiltonian path. In this way, you send your salesman into the network of cities, but now you don't really require that the salesman returns back to base. Probably in practical terms, it could be sufficient if the salesman then travels home. So the question of the Hamiltonian path problem asks, in a graph, is there a Hamiltonian path? So this is a more general problem. Also, the Hamiltonian path visits each vertex exactly once, which means that the number of edges is n minus 1. So there's also a connection here with minimum spanning trees. We have computed also Dijkstra's algorithm. We have computed shortest paths and graph. So again, in some sense, if you do not know the history of what everything that we have gone through this point, the NP completeness is kind of a little bit strange here. So how come for those problems that are very similar to the problems we have considered already, that there are no efficient algorithms? Okay, so the Hamiltonian path problem, for that problem, we do have an efficient certifier. And the proof of this lemma is almost identically the proof that we have covered for the Hamiltonian cycle problem. Again, we need to verify that the length is actually n minus 1. So we list all the vertices and only once. That can also be verified. And again, we have to check whether there is a connection between the two. Here we don't talk about data structures, so you can just have as the edges listed in a list and not at all structured, so you have to visit all the elements. That's a linear search. You can do better, but it is still polynomial time. Okay, now comes the important result. We will show that now that we have shown that the Hamiltonian path problem has an efficient certifier, we will show that the Hamiltonian cycle problem can be reduced to a Hamiltonian path problem. So any arbitrary instance of the Hamiltonian cycle problem can be reduced to the Hamiltonian path problem. Okay, so what we do is we construct a graph by replacing the vertices by two. So if there is an edge, we will replace this by a vertex, the vertex v by v prime, and there will be a v double prime, so we will actually replace every edge by actually that new vertex v double prime. So I don't have an example of this, and this should have been the last exercise. showing how to construct the graph from the Hamiltonian cycle problem into the Hamiltonian path problem. So we do have a Hamiltonian, if we have a Hamiltonian cycle, then actually we do have a Hamiltonian path in our G prime. If we have a Hamiltonian path, then actually we have this Hamiltonian cycle. And one way is very straightforward. If you have the Hamiltonian cycle, then you have these added vertices. So actually you have to replace them again. The Hamiltonian path problem leads to a Hamiltonian cycle in the original graph. So by the construction of this graph with the V double prime, if that replacement happens again, so the two different vertices, so you no longer have a cycle and then beginning and end are different, then you can see that you have the important equivalence. So what is also not stated here is that the construction from G to G prime happens in polynomial time. This is also not stated here, and that will be part of the fifth exercise of this lecture. Okay, to conclude, we have considered two very important sequencing problems, the traveling salesman problem and the Hamiltonian cycle problem. So the conclusions are stated here. So the two problems and the two main theorems that we have derived. If you have to remember anything from this lecture, is actually the general strategy and also the algorithms that we have used to rephrase, to encode the problems, one problem into another one. The tree satisfiability problem was here the important link uh, between the Hamiltonian cycle problem and the NP-completeness one. Graphs are important data structures. They, in their cycles, essentially can encode many information. Okay, I hope this lecture was not too confusing, and I will stop here. We have one more lecture to go where we consider partitioning problems, also as examples of NP-complete problems.